Hello everyone. In this video I'm going to talk about the last section on this chapter of the book. It's section 3.6 and it's called Capacitive Effects in a PN junction. So we have two different capacitive effects on a PN junction. One is the junction capacitance and one is the diffusion capacitance. Let's start with the first one. The junction capacitance is better seen at reverse bias. And if you remember, at reverse bias, whenever you're increasing this reverse voltage, you're increasing the width of the depletion region, and therefore you're increasing the amount of charge that's in that depletion region. And I have here written that this junction capacitance is due to the charges in the depletion region, right here. And let's see. For this, let's remember the basic definition of capacitance. Capacitance is the ratio between the rate of change in the charge and the rate of change in voltage. So what's happening here at the depletion region in reverse bias? So we are increasing the voltage, and that's increasing the width of the depletion region and the amount of charge. So you have an increase of the total charge in the junction. So your capacitance is equal to the junction capacitance over your reverse voltage. If you play with that, and not only your reverse voltage, remember that the voltage across your depletion region is actually your, and I have it right here, your reverse voltage plus the built-in voltage. So you have a change in voltage there. And that leads us to the formula. So if you were to play with this formula right here, you're going to arrive to and plug in whatever the junction capacitance, the junction charge was, and we look at that on the previous video. You're going to derive this equation right here, where this value is the junction capacitance when no reverse voltage is applied, and that is defined by this equation right here, and we know all the variables there. You have the cross-sectional area, you have the permittivity of free space, charge, the concentration of both acceptors and donors, and our built-in voltage. So this is a very easy capacitance term to understand. So you have a change on the charges stored in the depletion region that is due to this voltage, the reverse voltage, and since you're having a change in charges due to a change in voltage, you end up with a capacitance, a junction capacitance here. And the derived formulas are right here. Just the top two, the one in the bottom is the next one that we're going to look at. So now we're going to look at diffusion capacitance. Diffusion capacitance is a little bit more complicated, and it's only seen at forward bias. So let's look at the image right here. Right here I have a PN junction under forward bias, and remember that majority carriers here on the P side are holes, right? You have the majority carrier holes on the P side, and you have your majority carrier electrons here on the N side. And remember that the barrier is small, so they're diffusing from the highly doped side into the lightly doped side. So the holes are diffusing into the N region, and the electrons are diffusing into the P region. And let's see what happens with the holes first. I'm going to erase these majority carrier electrons here. When majority carrier holes on the P side diffuse into the N side, they become minority carriers on that N side. So these minority carriers diffuse and are first seen here close to the depletion region, right? And A similar thing happens with majority carrier electrons from the N side. They diffuse into the P side and they form minority carrier electrons near to the depletion region. Or they don't form, they become minority carrier electrons once they move into the P side. If you can see, the easiest thing to look at this is that you have an excess of minority carriers on both sides. They behave as parallel plates and they have a dielectric, if you want to see it that way, in the junction. So the depletion region is the dielectric and you have two parallel plates and that forms a capacitor, right? That's the easiest thing to think. Now let's look at the formula. So we have that a capacitor is, or capacitance is equal to the rate of change in charge over the rate of change in voltage. How do we find this rate of change in charge, of how charge changing? So remember that these minority carriers are here, but they want to recombine with the majority carrier electrons here on the inside. So you have majority carrier electrons, you have minority carrier holes. These holes, as they move into the inside, they start to recombine with electrons. And that takes some time. And this time is what we call minority carrier lifetime, in this case 4 holes. So that minority carrier lifetime is the average time it takes a minority carrier to recombine. So the time it takes this minority carrier hole to recombine with a majority carrier electron, that's called minority carrier lifetime. That's one time. So this is the time these charges take to recombine. As they recombine, the amount of charge changes, right? And let's look at the definition for current. You have current here. That's an amount of charge or the net flow of charge over certain time, right? So if we solve for charge, we have current times time. So if we plug that into our capacitance equation, we have capacitance being equal to current times time over a certain voltage. This time is going to be due to this minority carrier lifetime that we have right here, but not just the lifetime of holes. We also have a lifetime of electrons, and that's when electrons recombine, minority carrier electrons here on the p side recombine with majority carrier holes, so they have their own lifetime. And if we add those two lifetimes together, we end up with what we call mean transient time, which is this. And that's what we're going to have here for diffusion capacitance. We have a current. What is this current? Obviously, it's a current at forward bias, the forward bias current. That, if you remember, is basically the diffusion due to majority carriers. So we have this current, we have the time the minority carriers take to recombine, that's dt. And what is the voltage that generates minority carriers? If you remember that voltage is thermal voltage. So minority carriers are due to thermal voltage. And now with this, we derive the formula for diffusion capacitance. Is due to mean transient time over thermal voltage time the forward bias current. So let's try to review that a little more. So diffusion capacitance is due to excess minority carriers. So these minority carriers are formed when the majority carriers from one side move to the other. They become minority carriers on that side. Those charges are accumulated near the depletion region, so they're accumulated near the depletion region, and as they go or they move into the N-side, they exponentially decrease. So the concentration exponentially decrease as they move there. They decrease at a rate of current times time. So that creates a change in charge. That change in charge over voltage is what ends up being our capacitance right here. So just remember, for this chapter, that's everything I have for you guys. Is just a review. I encourage you guys to read more and look more into the formulas that's on your book. And we have two different types of capacitance or capacitances. In a PN junction, we have junction capacitance. That's better seen in reverse bias. We have diffusion capacitance. That's only seen on forward bias. And junction capacitance is due to the charges in the depletion region. Remember the bound charges. And the the diffusion capacitance is due to excess minority carriers. And just as a final note, just coming back to junction capacitance, if you look at this formula, junction capacitance is important because it's a variable capacitance due to a voltage. So if you wanted a variable capacitor, you just change the reverse voltage on a PN junction and you have a capacitance that's changing. And this is everything from this section, and this is everything from this chapter. So thank you.